All right, up to this point we've been talking mainly about derivatives, differential calculus. We've just started talking about antiderivatives, which has been leading us to the other kind of part of calculus, which is integral calculus. So as I mentioned at the beginning, there's differential calculus, which deals with the applications and the rules surrounding derivatives, and there's integral calculus, the two main branches. So we're going to talk about integrals today. This is the first time when you're going to kind of see what an integral is. Actually, it's not the first time you're going to see what an integral is, because you've actually seen integrals before, but you didn't know it. Now think about this. Let's go back to chapter 1 versus chapter 2, okay? In chapter 1, we talked about, this was one of the things we talked about, the limits as h approaches 0. You don't have to write this down. Just listen and remember with fondness. Right? F of x plus h minus f of x all over h. Right? And we put a little a value in there, so we turned that to f of a plus h minus f of a all over h. This was a limit, and what did this help us find? That represented what? What does that represent? Final's just around the corner. You guys got to know this. What is this? Oh, okay, before that, before the derivative. Not the tangent line, but the slope of the tangent. Yes, that's what I'm getting at. The slope of the tangent at x equals a. Okay. Now, if we actually put a number in a for a, we got a value of the slope. In chapter 2, we called this and you mentioned it already, this is the derivative. Okay? So we learned that there's a new name for the same thing that we've already known about. Okay? Now there's applications of derivatives. We talk about maximization and stuff like that. Right? Pay attention. Okay? So there's applications and there's rules. So we did applications. We did rules. Right? So in chapter 10, let's move down to chapter 10. What did we talk about in chapter... No, actually we got to go back to 9. Chapter 9, what did we talk about in chapter 9? The 9.1 was the antiderivative. Yeah. Okay. And in chapter 10, we said that antiderivative could be used to find what? Area under or between curves. Okay? Sorry, that's a mess of that. You're not writing this down anyways. So you see the progression. Here's the first half, really. And we did all the work up to basically chapter 9 here for differential calculus. Now we're kind of leading into what? Integral calculus. So chapter 11, if we follow this progression, guess what the integral is? Yes. The area under a curve is actually, we are just now going to call it the integral. Okay? Now, the indefinite integral, and you can write this down now, okay, is the expression for the area under the curve. The definite integral is the actual value of the area between A and B. So this indefinite integral, really it's kind of like the antiderivative, right? Evaluated at B minus the antiderivative evaluated at A, or I should say the indefinite integral is not evaluated, that's definite, but the indefinite integral is the antiderivative function, really. Okay? That's the antiderivative derivative. The definite integral is f of b minus f of a. So sometimes I take a long time to develop this, but I'm just going to kind of speed along the process here for you because it's really not that hard. And also, I'm going to come back to this, but if you look, there's a lot of parallels to the first part of the course, right? So the derivative, you know, f prime of x equals 2x plus 1. That's the expression, sort of like the indefinite derivative, right? And then if we have f prime at 2, right, we plug in 2 in there, and you get 5. So this is like the definite derivative. You see that? But we didn't call it that. And really we don't call it that, but that's the same sort of, it's the parallel there. Alright, so slope of the tangent actually is a derivative. We can find the expression for the derivative or the value of the derivative. The integral is actually the antiderivative. The indefinite is, you know, just the antiderivative statement, and the definite is the value of the area. So you see those connections there? Let me just get this all on one screen for you. Let me see if I can just fancy do this. Wow, look at that. Shrink it up. Okay, so there it is all on one screen. I know that's kind of small for you now to read, but this is really important that you understand this. It really is. I mean, we did this, chapter 1, we called it a derivative. Here we did this in chapter 9, we're now calling it an integral, basically. Okay? Any questions so far? So the area under a curve is also known as the, thank you, integral. Yeah. Hello, Wiki. Wake up. In chapter 11.1, it talks about the area under a curve, the area under the curve as a sum of rectangles. And we kind of talked about this, right? We used trapezoids there in chapter 10 to kind of approximate what the area under the curve would be. But if you use an infinite number of these little tiny rectangles, and as the number of them approach infinity, I guess, then you get the exact value underneath this curve. So they talk about the limit as the number of these rectangles approach infinity, and this sigma right here means sum, so we're going to add the areas of length times width sort of thing of all of these triangles. We are not going to do that. I think maybe in university calculus, you know, you work with this a bit more, but we're going to kind of skip this because this is sort of like the definition of what an integral is, and it's kind of like chapter 1 when we spend all that time on limits. Well, this is sort of where the integral comes from, okay? So we're not going to spend any time on that. You don't need to worry about this because we're going to kind of skip to the rules and the shortcuts like we did for derivatives in chapter 2. But I do want to talk to you about this here, okay? So there is a symbol for the integral, and you guys have seen this before in your text and in other places. This elongated x right here, so I'm going to zoom in a bit. I'm sorry, elongated s. I said x, I meant s. It's an elongated s, and it was introduced by Leibniz here, okay? And it is called the integral sign, all right? So this elongated s, and it's not an f that's missing a little dash in the middle, because that's kind of what it looks like if you look at this f. It kind of looks very the same, but it's not. It's an s. And the reason why Leibniz did that is because the integral is actually a limit of sums here, right? So that's why he did that. Now, bear with me for 1 second. I'm just going to copy this for you here, and here it is. So the elongated s is the symbol kind of right here, okay? So it's, you know, you kind of get used to practicing this. It's just an elongated s. Doesn't matter exactly how it looks. That's the symbol, and again, because the integral is a limit of sums, s for sums. In this notation, of course, the function itself is called the integrand. So this is the integrand, and you will want to highlight this in your notebooks when we copy this. It's called the integrand. the A's and B's, yeah, normal A and normal B. Yeah. Yep. The A's and the A and the B are the limits of integration. So there's a lower limit and an upper limit. They have integration there. And the dx, okay, the significance of dx, really, it's going to be used in 11.3. That'll be the last section that we do in this before the exam. But it's basically means with respect to x, just like in the derivative did. So it is part of the notation, though. Okay. So really, all this stuff right here, the elongated s, the limits of integration, this dx, that's sort of the integral sign. That's sort of the integral notation. And then the function is kind of separate in here, right? So all of this goes together. It is, it's a single symbol, so this means the same thing. The whole thing is, it has meaning all by itself, although you can pull the function out and it means something different. But this basically means the area between a and b under this curve f of x. That's what it means, the integral. Okay? So if the integrand is a positive function, the integral represents an area. Okay, we're going to quickly get to 11.2 because when we're doing the sums of these sort of things, it gets a little confusing. But I just wanted to talk about the notation there. So, okay, so that right there. All right. Let's go back to the text here, and let's move through this. So we're not going to do the addition. We're not going to treat areas above the curve and below the curve as positive or negative. We're not going to worry too much about that because in 11.2, this is important here. Again, we're quickly moving to the fundamental theorem of calculus. So on page 501, make sure you're there in your textbook. Let's take a look at the fundamental theorem of calculus. All right, the fundamental theorem of calculus basically means this, that if we have a function that is continuous, so we don't have any jumps or any asymptotes in the middle of this interval, but if this function is a regular function that's continuous all the way from the lower limit a to the upper limit b, then this symbol that we just learned here, the integral symbol, the integral means that we want to find the area. So we define this as the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So that's just what we got finished doing in chapter 10. And basically, here's the notation right here. That's just another way, another meaning for this right here. We'll do some examples. If we take a look at that quiz that we just had, okay, I asked you to find the area underneath the curve 0.5x cubed plus 2, underneath that graph, and above the x and to the x-axis for the values of x equals -1 to x equals 3. So what I was actually asking in that quiz was this: what is the integral from -1 to 3 of the function 0.5x cubed plus 2 with respect to x here, dx? That's actually what I was asking. And basically today, that's the big thing that you need to learn, is that the wording, find the area underneath the curve, or between the curve and the x-axis, this is another way of writing that, just like that. And of course, what that means is this: the antiderivative of f evaluated at 3 minus the antiderivative of f evaluated at -1. And also some new notation here for you. You can also write it like this, and I don't think you've seen this before, but this is another way to write this. Okay, so you just kind of write the antiderivative function, and then if you do this little kind of square bracket here, and you put the limits of integration, really, on the bottom and top there. That's another way of writing that. So you'll see that in your textbook, okay? And that's what it means. Now, this is important. The integral does not always mean area under a curve. That's what it's commonly used to find, okay? So it doesn't always mean that. But that's kind of the main thing that we're going to be talking about. All right. So, as we talked about at the top, the indefinite integral, okay? Indefinite, it means it's not definite. So the indefinite integral will not have limits of integration. So you won't have numbers at the top and the bottom of the integral sign. And you always need to put plus c at the end, like we used to do with the general antiderivative. Okay, so it might look something like this. Okay, so what does that equal? Well, we simply find the antiderivative of this function. We're asking for an indefinite integral, and so that one, like we did here, so it's 0.5 over 4 x to the fourth plus 2x, which actually simplifies to 1 over 8 x to the fourth plus 2x, right? And so there is your antiderivative plus c. You have to include that when it's an indefinite integral. Got it? All right. And of course, the definite integral, this is also the definite integral here. So when we have a number, okay, with these limits here, this number is going to be an actual value when you, and I think it's going to be this one, 18. 18. So that's the definite integral, the actual value of the integral in value. Okay? Got it? Pretty straightforward? Okay. So I think that's probably a good place to stop for there. I'm going to give you some questions to practice, and we'll talk about properties of integrals and that sort of thing. We'll do that tomorrow, but that's your introduction to integrals, what they are, a little bit of the fundamental theorem of calculus, which we will continue on the next lesson. Okay?